Okay, so we have officially learned all of the ways to solve linear systems. We've solved using graphing, we've solved using elimination and substitution. Keep in mind when we're solving a linear system that we're trying to figure out where two lines cross. So far, what we have done is we have seen where two lines cross, and they have always crossed at a point. So, graphically, what that looked like was we had two different linear equations, and again, I need to change these into slope-intercept form. So, what that will look like on the top one, if I subtract over the 2x and then divide by -3, it would be 2 over 3x minus 2. So I would have an equation, and I'll do this one in black. We have -2, and we'd go up 2 and right 3. So I'd have a line kind of like this. And my bottom equation, let's do that one in blue. If I subtract over the 4x and then divide by 2, I have y equals -2x minus 3, it looks like. So my y-intercept is -3. I would go down 2 and right 1, or I can go up 2 and left 1. But again, we can see that we have the lines crossing. This one, it's not super nice, but we can see that the lines cross. There'd be decimal answers. I'm not really concerned. What I want to stress right here is that this is what it looks like when we have one solution. That's typically the case. But anytime we solve for variables, we can see special cases pop up, and that's what we're going to talk about today. So if I move on to this second graph and solve for y, I would get something like this. I would get y equals, let's see, 3 over 6 would be 1/2 x, and then plus 2. So I'd have a y-intercept at +2. And if I were to go graph this, it would have +2 y-intercept, and we'd go up 1 and right 2. So my first equation would look kind of like this. Again, excuse the rough freehand drawing. You guys know that that's a little slippery here. The second equation, I would add the x over divide by 2. So once again, I'd end up with 1 over 2x. And then this time, unfortunately, it looks like I have negative 1 over 1/2 for a y-intercept. So to the best of my ability here, I'm going to try and graph this. Up 1, right 2 would be like this, I guess. Either way, we can see something special happen here, and we actually talked about this before. If I have two lines that have the same slope, I know that those two lines are parallel. And if two lines are parallel, that means that they don't touch. So one of our special cases is going to be what it looks like when I have parallel lines. Graphically, what that's going to look like is this. We're going to have parallel lines that don't touch, so if they don't touch, there's going to be no solution. Okay, the last special case, and you guys can probably guess because we've seen it before, but the top equation again, we have y equals -x plus 1. The second equation, if I subtract over the 2x and divide everything by 2, the second equation is actually the same exact thing, y equals -x plus 1. So now if I look at this graphically, I have +1 for a y-intercept, and my slope is down 1, right 1, and I graph my line. And again, excuse me because I know it's not going to be perfect, but it's the same exact thing for the blue line. So these two lines are completely the same. So when you see a picture like this and you have two equations that you just graphed, essentially when they lay on top of each other, it's the same equation twice. And what we can say there is infinitely many solutions. So graphically, when you guys see something like this, this is what you can see. Now, the one note you want to make here is the fact that both of my special cases in slope-intercept form have something going on. You can see that in both of these cases I have the same slope. Okay, in number 2, I have 1/2 for a slope. In number 3, I have -1 for a slope. So automatically, if you're graphing a linear system and you have two slopes that are the same, you should know that it's going to be one of your two special cases. That should be a red flag for you, and you should watch for those. So because we did learn more than one way this chapter to solve a linear system, quickly I want to show you the other two ways and what it looks like when you have either a no solution or an infinitely many solutions answer. So what I'm going to do is I'm going to start with elimination. Again, when we solve systems using elimination, we need the same equation twice, or excuse me, not the same equation, but the same coefficient, but the different sign. So what I'm going to do to start this one off is I'm going to change this top equation by taking it times -2. I want my coefficients, let's say x's, to cancel here. So if I rewrite that first equation, it's going to say -2x minus 2y equals -8. And if I solve and then if I just copy the second equation down, I can see that something kind of different is going on here. Pardon me, that's a y, not an x, equals 8. So if I look at this, -2 plus 2, -2 plus 2 is going to go away, -2 plus 2 is going to go away again, and -8 plus 8 is equal to 0. So essentially what I have here is 0 is equal to 0. Now again, we've seen stuff like this before when solving for variables. When we have variables and everything goes away, it's just like when I was only working with one variable. If everything goes away and I'm left with a true statement, because 0 is in fact equal to 0, if I'm left with a true statement, I'm again going to say infinitely many solutions. Okay, so your answer here isn't 0, or it isn't 0 equals 0, but it's infinitely many solutions, meaning that no matter what I plug in for x, 0 is always going to be equal to 0. So we don't need to go through the process of solving for y also. It's done. I know that no matter what I plug in for x and y, those two lines are going to be exactly the same. Okay, and on the other end of this, we have one more method that we've learned. We learned graphing, elimination, and substitution, so we're going to go ahead and do substitution. Just like we learned before with substitution, I have y isolated already, so what I'm going to do is I'm going to write equation number 2, but when I get to the y, instead of writing y, I'm going to write -x plus 3, and then I'm going to end up being able to solve for x. When I go to do this, I distribute that 2, so I have not plus, minus 2x plus 6 equals 4. And we can see here, 2x minus 2x is 0x. Well, 0x is just 0, so I'm left with a statement that looks like this: 6 is equal to 4. So again, just like when we were solving with one variable, if I'm left with something that is a false statement, I can say that no matter what I plug in for x or y, I can never make 6 equal to 4. So there is not going to ever be a solution to this system. Those lines, if I were to graph them, would be parallel. They're not going to touch. Okay? So again, nothing really new this lesson. We just are using things that we have already done, and once we get to a point, sometimes we're going to be able to still get a solution. Just because we learn this new thing where no solution and infinitely many solutions pops up has no meaning to us other than the fact that those things can happen. It doesn't mean that every single time they're going to happen. So in this homework, and for the rest of the time you are doing these on the test, quiz, or whatever, just keep in mind that the variables can cancel, and that means it's a special case. If they don't cancel, do what we've been doing. Solve for x, plug it in, find y, give your coordinate point answer. Thanks, guys, and have a good day.